So there are two parts to my talk. The first part, I'm going to give a summary of a paradigm or program which we have been involved in IUCAA for a decade or so, which describes space-time as a fluid. This is for those who have not listened to me on this topic earlier, the younger crowd, as well as a recall for others about what is going on. I would invite you to read the first section of this review article here. That first section is written for non-experts, just the first section one of this. Of course, you can read the whole of it if you feel like, but rest of it is technical. And that gives a broader description of what I'm going to say here. Also, I may not be giving the names of the collaborators as we go along, but all the due credits are given here, and I will also flash a slide right at the end regarding my collaborators. After finishing the part one, I'm going to do almost a vertical takeoff and go to part two, which is about a very recent work. This is, as you can see, is this 2011 on archive and 2021 publication in Physics Letters, where I'm going to show how ab initio you can get Einstein gravity from the microstructure of spacetime. This is a major new development, and which is just hot out of the oven, and more work is going to happen. Also, it is very technical. So I'll just quote the result and try to make it meaningful. Let us see how it goes. So the part one is essentially a paradigm shift, which has happened through the program which we have launched. It essentially says that the equations governing classical gravity have the same conceptual status as those describing elasticity or hydrodynamics. So if you take the equations of hydrodynamics and apply principles of quantum mechanics to it, well, you won't exactly get nonsense because you will get things like phonons and elasticity and their interactions and all that, but you're not going to get the atomic theory. So this is what we have been doing for 50 years, applying the principles of quantum mechanics to the equations of Einstein, which is as bad as applying quantum mechanics to the equations of hydrodynamics. It also implies, in fact, the main proof of this paradigm was that the entire space-time dynamics, which we have been taught, is a geometrical one, and you should use curvature and metric and things like that. The Einstein's equations can be rewritten completely in thermodynamic language, and Einstein's equation essentially tells you how space-time is getting heated and cooled. And this can be done. And this paradigm shift is the backbone on which everything else is built. So what is the key difference between a thermodynamic approach from a point mechanics approach? Let me just remind you that what seriously distinguishes thermodynamics from point mechanics is something called heat density. There is energy for any system, either a thermodynamic system or a cricket ball flying through the air. But thermodynamics also has something called free energy. And the difference between these two is the heat content of the system. Per unit volume, it is the heat density. It is temperature times the entropy density. So the entropy density is closely related to the information density. If information gets blocked, there is going to be some entropy density. This is how it comes up in gravitational context. It is also related to the microscopic density of states. What is important is that space-time, or rather each event in space-time, has a heat density. Let me stress that I'm not talking about black holes or horizons or any esoteric topic. I'm talking about an event right in front of your nose in this room or in the gravitational field of the Earth. There are observers who will attribute to this event a heat density. They will attribute a temperature to it. Entropy, you can sort of understand saying some information is lost or you coarse grained or something, but they will also attribute a temperature to it. So let me try to explain to you where this beautiful result comes from. For that, I have to go back to another beautiful result, namely the principle of equivalence. This is the key to the elegance of general relativity. What it tells you is that gravity is locally indistinguishable from acceleration. So let us compare two guys, one guy who is sitting on a chair near Earth and another guy who is freely falling. This second guy does not feel gravity and he is in a freely falling frame. And what is more important, you can do physics using special relativity in freely falling frame. You do not need gravity if you are going to work in freely falling frame. So locally, you need only special relativity. And that is a major boost because if you know laws of special relativity, then locally you can understand physics. Now, incidentally, if you ever had any doubt, general relativists are not crazy. Uh, if you read Resnick and Halliday, they will teach you that this guy is accelerating downwards with G, and this guy is not accelerating. By the time you learn GR, you will understand that this guy is not accelerating, he is freely falling, while this guy sitting quietly here is accelerating. Now, let me explain in slightly greater detail how this comes about. Here is a space-time, time and space, in some arbitrary coordinates. If light beams are emitted from this point, they follow some crazy trajectory because gravity bends light. Light beams are called null rays in general relativity. But if you go to a freely falling frame, special relativity applies in some local region and the light rays become 45-degree lines. In that freely falling frame, you can also have a guy who is sitting quietly and he will have a trajectory like this. So in this region, you can do special relativistic physics and ask what happens, what does this guy see compared to this guy? Then you end up getting a very beautiful result that the vacuum fluctuations in this freely falling frame becomes thermal fluctuations for the guy who is sitting quietly there. The temperature he attributes is related to the acceleration by g over 2 pi, except for fundamental constant. This result was due to two gentlemen, Davis and Andrew, in the mid-70s. But what is important is that, what is probably more important or more interesting is that recently I have been able to show that you don't need accelerated frames to get this result. I mean, usually for those in the audience who know these things better, this result would have been derived by using something called Rendler frame, uniformly accelerated frame, etc., etc. You don't need any of this. You can just use special relativity and look at the Feynman propagator and obtain this result. So there is a temperature associated with gravity. To stress this point, if you are not feeling freely, most of the time we are not feeling falling freely, you will experience gravity. You will also associate a temperature to the space-time events, which means that there is a deep connection between gravity and thermodynamics. Now, why is this important? This is important because if you have a glass of water, you could have figured out that it is made of discrete atoms without ever experimenting it at angstrom scales to see the atoms. This is precisely what Boltzmann did, and others gave him a hard time. He said that if something is hot, it must have microstructure to store energy. So this is what he showed, and what is more, he actually gave a formula for that. He said that the number of microscopic degrees of freedom you need to store an energy E at a temperature T is given by this equation. As often it happens, we teach kids this equation completely the wrong way around. This is the way that equation has to be written. This is because it tells you something paradoxical. On the right-hand side, E and T are thermodynamic variables. It can be defined in the thermodynamic limit. The left-hand side has absolutely no thermodynamic interpretation. This is the actual number of microscopic degrees of freedom is actually infinite in the thermodynamic limit. This is the wrong way in which we write this equation, but that is historically, that is how it happens. So let me go with this. But it relates macroscopic thermodynamics to microscopic statme, which means that if I know the macroscopic thermodynamics of space-time, I can have a handle on the microscopic physics of space-time. This is exactly what we will do. It turns out that this particular equation is also the gravitational field equation. If this equation applied again and again and again, that gives you 10 equations of Einstein. for static spacetime. I'll talk about dynamical spacetimes in a minute. What it means is that you take a region of spacetime, normal three-dimensional region of spacetime, bounded by a equipotential surface of gravity. Then you can show that the bulk source of energy for gravity is related to the surface degrees of freedom in this surface, which is just the area of the surface divided by Planck length square. So there are 10 to the 66 units per square centimeter. And the average temperature. The average temperature you define because at any given point here you have a stationary observer and a freely falling observer. Relating these two, you get a temperature, and that temperature is what appears. Now let me try to make this less mysterious, but by showing you how a +2 student could have derived this, if only he knew the relation, he or she knew the relationship between temperature and gravity. So this is just Newtonian limit, where you have del square phi Newtonian potential is equal to divergence of the gravitational acceleration is equal to 4 pi g rho. Let us first write rho mass as rho energy upon c square. Then write this in terms of rho energy. So the energy density which is producing the gravitation is related to the divergence of g by this. Integrate both sides over a volume bounded by an equipotential surface. So Gauss theorem, and this is just g dot n, but because it is an equipotential surface, the vector g is minus in the direction of n. So this is just magnitude of g. And left hand side is the energy. So you get this equation. Completely classical, no h cross inside. Now what you do is to multiply and divide by c over h cross by hand. This quantity is just the Andrew Davis temperature. And this quantity beautifully combines to give you a factor half because it is half kT and an 1 over LP square. So you get this result. This is exactly what I wrote down. You take the area of the equipotential surface, divide by LP square, and then multiply by the average temperature, and that gives you the energy. So you see, in something like 90 seconds, using +2 physics and one relation from Andrew and Davis, you can show that there is a deep thermodynamical connection in gravity. And this does, if you reverse engineer this, you will get Newton's law. So Newton's law can be stated entirely as a thermodynamic principle. That is, Newton's law of gravity can be stated entirely as a thermodynamic principle. What is surprising or interesting is that with a lot more complicated mathematics involving Killing vectors, blah, 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 it can be derived for all static spacetimes. Well, what happens if you go beyond static spacetimes? Okay, this is just for those in the audience who are not scared of too many integers. It turns out that what is conventionally taught as geometrical variables, like metric tensor multiplied by this, and these are Christoffel symbols, a particular combination of them. These variables have a pure thermodynamic interpretation. If you take suitable dot products and think of Q delta P and P delta Q, they can be interpreted as S delta T and T delta S. And in a time-dependent spacetime, what happens is that some kind of a time derivative of this momentum and energy here will be related. This can be interpreted as heating of spacetime or cooling of spacetime to the difference between n surface and n bulk. When n surface is equal to n bulk, which is exactly where the equipartition theorem, which I wrote down before, applies, then the left-hand side is 0. And that is like saying that if there is I called it holographic equipartition because it is equipartition and also it gives a relation between surface and bulk. So this evolutionary equation is described entirely in geometrical, entirely in thermodynamic language, because this can be written in terms of TdS and SdT kind of a thing. So this is equivalent. It implies and is implied by Einstein's equation. There's a single equation which implies all the 10 equations because this is supposed to hold on every surface which you are integrating out, and that has sufficient power to show you that this is equivalent to Einstein's equation. Okay, so this is roughly what I wanted to say in the first part. Now I want to go deeper. The question is, can we get the correction to Einstein's equation due to the quantum microstructure of spacetime? I have used the thermodynamics, invoked Boltzmann, and told you that there are microscopic degrees of freedom. I have even counted for you the number of microscopic degrees of freedom, which is area divided by LP square in some region. So obviously there is some kind of discreteness at Planck length scale is involved, and you have to do coarse graining over that. Can we use these ideas to actually build it better? Here, as I said, this is going to be more technical. What you want is that there is an action principle from which gravity can be derived, which has a Lagrangian. You want to write down an effective Lagrangian, which takes quantum corrections into account. So what is going to happen is that the Einstein Lagrangian is the Ricci scalar divided by 6 pi g, and g in dimensionless units is LP square. This A effective is dimensionless. It is a conventional action divided by h cross, and that is the way high energy physicists would like to look at. So this term multiplied by 1 is the conventional Einstein's theory. And I'm trying to compute the correction to this, which will be of the order LP square R. They will vanish when LP goes to 0 in the classical limit. So for that, you need an extremum principle. And since we are using statistical mechanics, there is a natural extremum principle. What you need to do is to take the number of possible configurations of microscopic pre-geometric degrees of freedom of spacetime associated with a sum even p consistent with a given geometry. This is just like saying that think of the number of microscopic configurations of molecules in a box of gas consistent with macroscopic constraints like the volume, pressure, etc. And then you maximize the total number of configurations consistent with a mesoscopic scale geometry, because we are assuming that the semi-classical description applies at a scale which is somewhat larger than the Planck length, because as soon as you go to Planck length, it is like looking at a fluid at a scale less than mean free path. You cannot use a fluid description there. So you are assuming that there is a mesoscopic scale in which these corrections apply, and that is obtained by maximizing this omega. So mathematically, you have some number of configurations associated with a given event, and these are some microscopic pre-geometric degrees of freedom. And you multiply it over all p and psi, because this is what happens at one particular configuration, and you multiply this. So you play the same game that you take the logarithm of that, and so it can become a sum in the exponential. And if you just do the summation over p, that becomes in the continuum limit integration over the space-time volume. And what is involved is the logarithm of this f integrated over a suitable measure of pre-geometric variables. So this is what I have to find. Now, remarkably, this can be found with very few assumptions. If I get time in the end, I will highlight why this is almost assumption-free. The constraints or guiding principles used to obtain this are to leading order one should get Einstein gravity, but it should come as a result, not as an assumption. I am not assuming Einstein's theory and then computing its correction. I'm going to get at one package Einstein's theory plus all its quantum corrections together. Second, the expression for L effective should be generally covariant, and the discreteness at Planck scale should be incorporated with suitable coarse graining. And if the metric depends on the coordinate system you use, and so if you gauge fix the coordinate system, this is a technical term, the density of microscopic degrees of freedom must have a simple interpretation. And what I mean is that it should scale like the volume of the spacetime. If you do all that, you can actually write down what is that L effective. And as I said, I'm not going to give you the details of the derivation. You should go and read the paper for that. What comes out can be expressed in terms of two new variables, not new, it is historically very old, but it is not usually taught in GR courses. The first is something called a geodesic interval. This is the geodesic distance between 2 points x and x prime. To take two events which are quite close to each other, so that there is a unique geodesic connecting these 2 points, and you calculate the length of the geodesic, which is computed like this. So this gives you the geodesic interval. What is important is that this contains exactly the same information about geometry, because given the metric tensor, I can obtain this quantity. This metric tensor gives you this quantity, and given this quantity, there is a formula which will give you the metric tensor. So they contain the same amount of information. But this is a lot more conceptually clearer quantity to work than with metric. To begin with, it is a biscalar. So if you fix one point, it is a scalar. You don't have to worry with 10 indices hanging around here. I mean, indices taking some 10 different values hanging around here. And it is completely covariant because it is a covariant scalar. And you can work everything out in terms of that. Using this, you can define something called a Van-Vleck determinant. This is ubiquitous in physics. Whenever you do WKV approximation, you get that. And those who do gravitational lensing, there is a lensing matrix which one uses and which is very closely related to this Van-Vleck determinant. The lensing determinant, which sort of tells you the shear and magnification, etc. So this is obtained by taking the sigma square, taking two derivatives, and taking the determinant on this A and B, and then just divide by root G and root Gx for proper covariant behavior. Now, once you have done this, it is a function of two events. You can rewrite it in terms of geometrical variables collectively denoted as the curvature. And from one point to another, since there is a geodesic, you have a geodesic distance and the initial direction in which the geodesic starts. So there is a sigma, ni, and all the geometrical variables in which delta can be expressed. The answer to the question as to what is the effective Lagrangian is, take the log of this delta and integrate it over these internal variables ni over a unit sphere. You do this and you divide by the coarse graining scale, which is essentially the Planck scale. So this is the effective Lagrangian. So what we did gravity with using r root minus g, we should now do it with this. If only you can write an explicit expression for this in terms of geometrical variables, it would have been great. Unfortunately, nobody knows how to write down the Van-Vleck determinant in terms of these objects. We have an indirect definition, but as you know, the definition first involves getting the metric, computing the geodesic distance, then taking the Van-Vleck determinant and inverting it and writing it in terms of geodesic distance. This is a highly nonlinear, non-trivial process. But in principle, it can be done, which means that in principle, I have now the effective Lagrangian for gravity incorporating all the quantum effects, because this coarse graining of this system has introduced this length L, the Planck length, into the system. However, all hope is not lost, because people know perturbative expansion of this quantity. So just to show you how complicated things can be, the perturbative expansion, which is usually quoted for delta to the minus 2, is sigma square, sigma cube, sigma 4, etc. to order sigma 5. And this has various coefficients which can be expressed in terms of curvature quantities. So you can take this and evaluate it perturbatively. If you do that, you get the answer I promised. You get the Einstein action or effective action, E can stand for both, which is the zeroth order term, which is Einstein-Hilbert action, this upon 6 pi LP square. Then you get corrections. So I have just to spare you some ordeal, I didn't write the LP to the power 4 correction. You can write it down. The LP square correction is LP square times a quantity Q, and that Q is this, which is entirely expressed in terms of curvature quantity. So by now, you can vary this. You can vary this quantity. And people have written down actions of this kind, not this, but actions involving derivatives, curvature components, and all that. And they have written these actions down and they have varied it. So in principle, you can vary this. And when you vary this, you get quantum correction to Einstein's equation. So that is almost the end of my talk, which I have called the new beginning. This formalism which has been developed, this paradigm is powerful enough to give Einstein's equation and Planck scale correction a bin sure. I did not start with R root energy and compute its quantum corrections. I gave a principle based on microscopic combinatorics, and that gives you an action, and that action has a leading term which happens to be R over 16 pi g, and it also gives you the corrections. And at a fundamental level, it tells you that the description by metric and curvature should be replaced by that with sigma square and delta. So sigma square, is metric, and two derivatives of the sigma square is what is used to construct this. So this is more like curvature. So this is what we need to explore further. And I'm very happy with this because it shows that the previous part one paradigm was essentially taking Einstein's equations and giving it a thermodynamic interpretation. That is beautiful. And it is a new insight. And it tells you a lot of things about classical gravity itself, which you never suspected. But now you are going further. You are actually seeing glimpses of something like the kinetic theory of space-time atoms, not just the thermodynamic limit of space-time atoms. I'll stop there. I'll just keep this slide on. Um, this work was built over PhD theses of several students in the past who are all contributed one way or the other. I have given their current affiliations here, and those in red have, they were students at some stage and now they have faculty positions. There were two postdocs and others I have indicated that. And for your benefit, I have repeated the two papers. This paper is highly technical, but I would invite all of you who are not even in this field to read at least the first section of this paper. Thank you very much.